let's work some examples of doing definite integrals. Our first problem is going to be problem 9. They're telling us that they want us to find the area under the function y equals x minus x squared. Now, they didn't actually give us any limits of integration here. So let's go ahead and look at the graph of this thing. So we have this parabola, and the book actually has a picture of what they want here. They make it kind of clear from the picture that they want the part of the parabola that actually goes positive. This section here. What is the area under this curve in this region? We're going to have to actually get our limits of integration from that. We're going to have to figure out where exactly does this hit the x-axis. Well, just from here, you can already see it's probably going to be 0 and 1. And looking back at our function, of course, 0 and 1 make this 0. So obviously 0 makes it 0, but 1 makes it 1 minus 1, which is also 0. So our limits here are going to be 0 and 1. We're not going to be doing a lot of problems where we have to find the limits in today's lecture, but we will be seeing a lot of that in the next one, in section 5.5. So we want the definite integral from 0 to 1, those are the limits that we got, of this function. And say that the area is equal to that definite integral. To find this integral, we're going to use our fundamental theorem. That means that we need to find an antiderivative of x minus x squared. In other words, we're kind of just finding the indefinite integral of x minus x squared. This indefinite integral is something we've been working on in the previous sections. We're going to use our familiar power rules. So here, this x to the first power, we raise that power to 2. Then we divide by the new power. For x squared, we raise the power to a 3 and divide by that new power, get a 1/3. We solve the minus sign. And then we have a plus c. That's the indefinite integral. For the definite integral, we're going to have to use this antiderivative. Technically here, any c will work. Any c will give you a new antiderivative. We'll just pick c equals 0 to be the easiest. Leave off that plus c, essentially. Because we're only looking for one antiderivative. And all of them will give you the same result overall. The notation that we're going to use here is we're going to put the antiderivative that we have here in brackets. And then we're going to take the limits of integration and put them on the back of the brackets. This is an indication that we haven't applied the limits of integration to this antiderivative just yet. In other words, we're using kind of a notation here where we put the capital F of x, we found that antiderivative, and we still need to apply a and b, and that means that we take our top limit here, this b, put it into this function first. Then we take the a and put it into the function and subtract the results. In fact, this notation is actually a little bit more general than just working with integration. People will use this when they want to do something where there's a difference between two values of the same function. In this particular case, we get to go ahead and put in the 1 first. I'll put 1 in for all our x's. So we have 1/2 times 1 minus 1/3 times 1. Then I get to put 0 in. Get 1/2 times 0 minus 1/3 times 0. And then it just becomes a matter of adding things together, or adding and subtracting things. Of course, the zeros here don't really matter. 1/2 minus 1/3. We combine fractions there, we get a 1/6. That is the area contained in here. And if we actually want to check ourselves, the GeoGebra does have an integrate or integral command. We go ahead and put in. I'm just going to use the letter F because that's what it named this particular curve. And I'm going to say the integral of that function from 0 to 1. It'll even give you a nice little shaded in region, showing that it is representing that area. And 1/6 is about points. Well, 1/6 is 1.166666 and so on. So I just rounded it to 0.17. Let's go ahead and move on to problem 11. This is a similar problem, but since we've kind of already introduced some of the notation, some of the ideas about how we're going to approach these problems, this will go a little bit faster. We're going to take another area. This time it's under the curve y equals 1 over x squared. We're saying between, specifically, 1 and 2. So this time they actually gave us our limits. Partially that's because this function actually never hits the x-axis ever. We're going to go ahead and put in our limits, x equals 1 and x equals 2. We end up with this region right here, the area underneath this curve between those two x values. So we are trying to find an area again. But again, it really is just we're set up the definite integral from 1 to 2 of the function 1 over x squared dx. First thing that we're going to do, because we do need to take an antiderivative of 1 over x squared, we'll turn this into just x to the negative 2 power. Then we're going to find the antiderivative of x to the negative 2. Remember here we add 1 to our power, so our new power is negative 1, and then dividing by the new power, we just get a minus sign. I'm putting that antiderivative in brackets, though, because we still need to apply the limits of integration. We go ahead and plug in 2. So we saw that negative, but we have a negative of 2 to the negative 1, but that is just a 1/2. Minus this minus is from the Fundamental Theorem of Calculus. This minus is the minus that we have here, and we plug in 1. So 1 to the negative 1 power is still just 1. In other words, we have negative 1/2 plus 1. In other words, we have 1/2. So these problems can actually be rather quick once you get used to the ideas behind them. Once we already know how to take the antiderivatives. Hopefully by this point you've gotten kind of used to those. You've done enough problems that those don't take you a long time to do. At least for the simpler ones, like just a single power, at least. And now all it really comes down to is knowing how to put those limits into the problem. We can go ahead and find the integral here as well. Integral of the original function f from 1 to 2. And of course, like we saw, we expected an area of 1/2, and they gave us 0.5. Same thing. So let's move on to problem 20. This time they're just giving us a definite integral. They're not actually giving us an area. We want the definite integral from negative 2 to 0 of the function 4x plus 9 dx. And this is rather straightforward. We just take the antiderivative 4x plus 9. Remember here, x becomes an x squared, but we need to divide by the 2. 4 divided by 2 just leaves us with a single 2. A plus 9 here means we get a plus 9x. And we still have to apply the limits to this particular antiderivative. When we plug in 0, well, both those terms are just 0, so I'm not even going to write them both out. Then we subtract what we get when we plug in negative 2. We have 2 times negative 2 squared, well, negative 2 squared is a positive 4, plus 9 times negative 2. If we work those out, this is an 8, this is a negative 18. 8 minus 18 would be a negative 10, but we have a minus sign there. So we have a positive 10. This actually can be interpreted as an area. If we go ahead and graph the line 4x plus 9, we have this line here. We're going between x equals negative 2 to x equals 0. So we're looking at what's underneath this line between these two lines. This is actually what we call a trapezoid, if you want to be more geometrical about it. It is a region that has two parallel lines. It's a four-sided region that has two parallel lines and then two not so parallel lines. It's not a parallelogram. And there is a formula for finding the area of such a thing. And I'm not going to get into that formula. Maybe we'll come back to it later on when we do some more numerical stuff with integrals. But just be aware that we could actually find this area using geometry rather than having to use an integral. And if you do that, and I'll leave it to you to do that, if you want to, we can find that the area, in fact, is 10. It is consistent with geometry. At least it better be. Otherwise, what was the point of doing any of this? In problem 25, this is somewhat similar. We're just taking a definite integral. This time, we have a little more complicated of a function. But at the same time, it's not too bad. We have the integral from negative 1 to 1 of the cube root of x minus 2. We'll go ahead and rewrite our cube root as an x to the 1/3 power. And I just noticed that I switched to using x's. The book was actually using t's. Let's stay consistent with the book. Okay, so we have the integral from negative 1 to 1 of t to the 1/3 power minus 2. We take our antiderivative the way we know how to. The 1/3 power, we add 1 to that. 1/3 becomes a 4/3. We need to divide by the new power. In other words, we're multiplying by the reciprocal of 3/4. Minus 2 at the back becomes a minus 2t. And we still have to go from negative 1 to 1. We plug in our top limit first. When we plug in 1 to the 4/3 is 1. So we get a 3/4 here, minus 2 times 1. Then we subtract what we get when we plug in negative 1. We still have the 3/4, and negative 1 to the 4/3 is still a positive 1. That 4, remember here, that 4 is actually, you can think of that as the 4th power of the cube root of 1. And so that 4th power is going to get rid of any negatives. So we are still going to have a positive 3/4 here. Then we have negative 2 times negative 1. They'll turn into positive 2. And then notice what happens here. The 3/4 actually cancel each other out. The negative 2 and minus a positive 2, those actually combine. We get a negative 4. So notice here that we did actually get a negative number from this integral. That means that this definitely cannot be representing just an area. In some ways, at least, there has to be some negative areas. Maybe we'll go ahead and graph this one as well. So let's take the cube root of x. GeoGebra wants us to use x's, so we'll go ahead and do that. Minus 2. We're going from x equals negative 1 to x equals 1. So we are actually looking at this region here. It's completely below the x-axis. And so you could say that the area inside of this region here is 4, but it's below the x-axis, so it's a negative 4. In fact, we can go ahead and just do that. A equals negative 4. The area of this thing is negative 4. Alright, now we move on to problem 31. Here again, we just have a definite integral. We have the integral from 0 to 4 of 1 over the square root of 2x plus 1. So we have a substitution problem. We're going to need to make a substitution to find the antiderivative of 1 over the square root of 2x plus 1. It's not a very difficult substitution, because we don't want to jump right into the more difficult stuff right away. But we are going to have to make a substitution here. So we'll let u equals 2x plus 1. That means du is 2 times dx. And since we don't have a 2 in here already, we'll go ahead and divide the 2 to the other side. That means we can go ahead and, well, we have 1 over the square root of u, because we're replacing 2x plus 1 with the u. The dx is going to be replaced by 1/2, so we'll put that out in front, and a du. The problem is, what do I do with my limits? We can't just put the limits of 0 and 4, because those are limits for x. Those are values of x. If we're not using x anymore, it doesn't make any sense to use the same limits that we had before. We could actually stress the fact that we are specifically working with values of x by putting in the more complicated x equals 0 to x equals 4. That's just a sign to us that these are not the limits for u, but instead we do have to go ahead and eventually substitute back for x, like we were doing before when we were finding antiderivatives. But there is actually a clever thing we could just do. We could instead find what values of u make sense. Basically, what is u when x equals 0? If x equals 0, what does u equal? Well, we have a formula for u in terms of x. We can go ahead and just plug in x equals 0 and see what our value of u is. So we take 2 times 0 plus 1, which is just a 1. When x is 0, u is equal to 1. Same thing when x is equal to 4. U is 2 times 4 plus 1. That's 8 plus 1, or 9. So as x is going from 0 to 4, u is going from 1 to 9. And we can go ahead and just use those values as our limits. So this integral that we have up here is equal to 1/2 of the integral from 1 to 9 of 1 over the square root of u du. And the advantage of doing this is that now we never have to go back to x's at all. We never have to do the step where after we find the antiderivative, we put in the values of x back instead of our u's. We're going to go ahead and actually, instead of rewriting this integral again, let's just turn the 1 over the square root of u into the u to the negative 1/2 power. Because we need to have it in terms of a power in order to find the antiderivative easily. So we have 1/2. We have all that stuff. Now what is our antiderivative? We add 1 to the negative 1/2. That gives us a u to the positive 1/2. And then we divide by 1/2, or in other words, we multiply by 2. Actually, we can even say the 1/2 and the 2 cancel out. This is just the square root of u. So in fact, our antiderivative here was just the, if you incorporate the 1/2 here, it was just the square root of u. So we go ahead and plug in 9 first. So we have the square root of 9 minus the square root of 1. Or 3 minus 1, and we have 2. So of course the point here is knowing how to actually do substitution at the same time as a definite integral. Let's do another problem like that. Let's work on problem 37. Here we have the integral from 0 to 2 of x over 1 plus 4x squared. Again, we have an inside function. The 1 plus 4x squared is something that we'd like to have be a single variable. So we'll go ahead and set u equal to that. The derivative of u is just 8x. So we have du is 8x times dx. We do have the x. This wouldn't work if we didn't have this x here. In fact, this is a rather difficult integral to do if we didn't have the x on top. Technically, it's actually flat out impossible to do unless you have trig functions. So but we need to deal with the 8. The 8 we're going to have to move over to this side. Oops. Don't forget that x dx. And so we're going to introduce a 1/8. I'm just going to stick in front. The x dx is just going to turn into our du. And then the 1 plus 4x squared on the bottom is just a u on the bottom. Our limits we're going to have to change as well. We need limits in terms of u instead of in terms of x. So when x is equal to 0, what is u equal to? We just plug 0 in here. U equals 1 plus 0, or just u equals 1. When x equals 2, we plug that in here. We have 1 plus 4 times 2 squared. 2 squared is 4. 4 times 4 is 16. Plus 1 gives us 17. Now we need an antiderivative of 1 over u. Remember, the antiderivative of 1 over u is the natural logarithm of the absolute value of u. Now, in this particular case, since we know that we're not going to be plugging any negative numbers into it, our interval here does not include any negative numbers, then the absolute values are kind of unnecessary here. But there's not really any harm in putting them either. Go ahead and plug in 17 first. We have the natural logarithm of 17 minus what we get when we plug in 1, the natural logarithm of 1. There's not too much we can do with the natural logarithm of 17, but the natural logarithm of 1 is always 0. That's just a particular value that's worth knowing. Natural logarithm of 1 is 0. So we can go ahead and take out that part and just say that we have 1/8 of the natural logarithm of 17. So kind of interesting. The natural logarithm of 17 is not something you probably expected to have in the formula for the area. Well, it is an area. We can go ahead and actually plot it. Let's go ahead and even do that. We had x over 1 plus 4x squared. We're going from x equals 0 to x equals 2. In fact, we can just go ahead and write the integral of f from 0 to 2. So we have this region here. And probably wouldn't guess that somehow the natural logarithm of 17 was involved in there. Kind of interesting little fact. Let's go ahead and do one last problem. we're going to work on problem 54. This is a slightly different problem than the ones we've been doing, because it's not just a evaluate this interval. What we're doing here is finding the average value of the function f of x is equal to x cubed on the interval 1, 3. Of course, if we're trying to average this out over all numbers, that you could run into some issues there. We definitely don't want to be going over all real numbers entirely, just on the interval from 1 to 3. We go ahead and just go ahead and plot that. We have x cubed is equal to this. We're going from 1 to 3. I'm going to shrink my y-axis. So I might even go ahead and expand out my x-axis. So on this interval, what is the average value of this function? Think it's somewhere in the middle, but where in the middle? Would it be further down, higher up? What do you think? Well, we have a formula. Remember, our formula for the average value of a function was equal to, we took the definite integral of the function from a to b, but then we divided it by the length of the interval, 1 over b minus a. So in this particular example, our b is 3 and our a is 1. So we have 1 over 3 minus 1. Then we have the integral from 1 to 3 of x cubed. Of course, we can go ahead and simplify this. This is just 1/2. Here we need to take the antiderivative. The antiderivative of x cubed, we raise that cube to a 4th power and divide by that new power. But then we also have to evaluate this antiderivative at 1 and 3. We can go ahead and move the 1/4 outside. We have 1/2 times 1/4 is 1/8. We go ahead and take 3 to the 4th power. 3 to the 4th power is 81. Minus what we get when we plug in 1. 1 to the 4th power is, of course, just 1. And then things actually are kind of nice here. 81 minus 1 is just 80. 80 divided by 8 gives us 10. So what that's saying is that if we look at y equals 10, this is the average value of our function on this interval. On average, we're about equal to 10. Geometrically, what this means is if I look at the area under the cube from 1 to 3, it has an area of 20. If I look at the area of the rectangle, so I'm just going to go ahead and do the integral of 10 from 1 to 3. That's the area under this of this rectangle that I've made here. It also has an area of 20. Those are both the same area. And again, I'm not going to get really into why we're using this idea for taking average values. It kind of more comes down to being able to interpret integrals in terms of sums, and we're going to be talking about that in a few sections. But the point is here that at least it should be relatively okay to think 10 is a reasonable number for our average value. But I'm going to leave this video here. Hopefully this is giving you a good idea of how to work with definite integrals. Is really not too much more than what we're doing with indefinite integrals. But we do actually already have applications of the idea in terms of areas and average values, in fact. So we've actually made a major step, made some big progress here. But next time we'll talk about how we can find a little bit more general areas rather than just ones that are under functions. It won't be too much of a stretch for what we're going to do. We're just going to kind of incorporate more than one function at a time. But we want to be able to look at areas in general. So I'll see you guys in that next video.